Welcome to the API Academy video series. You're currently watching the Introduction to OAuth 2 video. By the end of this video, you'll be able to explain the purpose of OAuth 2 as a framework for authorization, describe the authorization code flow, summarize and compare 4 different authorization grant types, describe the current challenges of OAuth 2 implementation. OAuth 2 is an industry-standard authorization protocol that permits a user to grant an application access to a protected resource without exposing the user's password credentials. An OAuth access token is issued and accepted for user authorization at the API endpoint. On the traditional browser-based web, access control methods generally assume the presence of 2 parties, the client and the server. Because the HTTP protocol includes specifications for basic authentication in this scenario, the core mechanisms for effective access control are already in place. As organizations began exposing APIs to third-party apps, these mechanisms proved inadequate, as access control now involved an extra party, the app user. For example, when a social network allows an external developer to create an app for its service, users may not trust that app enough to give it their login credentials that the app needs in order to be useful. There is an issue with having multiple parties in access control. OAuth is an open standard for authorization, designed to address this type of problem. It prescribes a standardized way for the end user to grant third-party applications access to their server resources, without sharing any credentials, putting the user in control of delegating access to an API and allowing one service to integrate with one another on behalf of that user. Let's look at this from a different angle. When you want to buy something at the store, you somehow need to grant the store owner access to your money. You could pay by cash, but in this case, we only have a credit card on hand. Do you just want to tell them your PIN number? No. You want to enter it yourself. Your resources are yours, and naturally you want to protect your resources. The API world works in the same way. If you're the owner of the resource, and an application wants to access the resources you're willing to share, in response, you'll grant the application access with your credentials. At the same time, however, you don't want every app out there to use your credentials and get full access to your resources. As an example, let's take a look at the OAuth 2 authorization flow for the authorization code grant type. 3 other grant types are also supported by OAuth 2, but we'll talk about these later. There are 3 main roles that we will look at in this simplified authorization flow: the user, Jane, the third-party application, CoinApp, and a major bank called Piggy Bank with its API service. In our example, Jane wants to use the CoinApp application to be able to access her banking information such as payment transactions via the Piggy Bank API. First of all, the application developer needs to register the app with the bank through the API service that the bank provides. The API needs to know the application name and the callback URL for redirections. The API then provides the app with a client ID and a client secret. The client ID is a public identifier for apps and is typically encoded in a multi-character hex string. The client secret is a secret known only to the application and the authorization server. Secrets can be generated as a 256-bit value and then converted to a hexadecimal representation by a cryptographically secure library. It's also important to note that the resource scope that CoinApp is permitted to access is determined here at registration. API program administrators at Piggy Bank will decide the appropriate scope for third-party entities like CoinApp. We'll discuss scope a bit later in this video. 2 other important components of the flow are the authorization server and the resource server. In our example, both servers belong to the bank, but the role of the authorization server can also be delegated to a social login platform such as Google or Facebook. We should also note that Piggy Bank already has predefined how end-user consent will be managed in the form of access tokens. The access token is critical to determining what an end user, in our case Jane, can 1. Access in its resource server, and 2. What Jane can do with those resources. However, before the app can even get its hands on that all-important access token for Jane, there's a few other steps that must be completed. First, Jane logs into her CoinApp application and wants to be able to access her banking information via the piggy bank API. Recall that the application has no direct affiliation with the bank. It's a third-party entity. The application sends an authorization request to the bank's authorization server. It redirects Jane's browser to the login screen of the authorization server. The authorization server asks Jane to authorize CoinApp's access to her bank account. If the authorization server is a social media account, Jane may be asked something like this. CoinApp seeks to access your transaction history and account balances. Do you allow it? Jane has the option to grant or deny access. In this case, Jane grants access to CoinApp. Next, the authorization server grants the application an authorization code. However, note that the authorization code alone is not enough for the client application to fetch the requested resources from the resource server. The application then exchanges the authorization code for an access token from the authorization server. This token contains a scope, which gives the application only the permissions that Jane granted. Granted scopes inside the access token can limit access to a subset of protected resources. Scope is a mechanism in OAuth 2 to limit an application's access to a user's account. The scope may be restricted to account balance or a list of past transactions only. Nothing else in the bank's resource server may be accessed. In the scope, Piggy Bank can also restrict what the client app wants to do with the resource. In the case of our CoinApp application, we have three scopes defined by the API designers at Piggy Bank. They are transaction history, account balance, and account transfers. Per the bank's API policies, the access token issued by the Piggy Bank authorization server for Jane's resource use case is restricted to transaction history, account balance, and account transfers. This means that through the CoinApp, she's permitted to read or get her transaction history and account balance, but is also able to make account transfers, in other words, updates, as required. In their API documentation for client app developers, Piggy Bank will have a clear description of the permitted resource types and permitted actions for the available scopes. Here's a really simple snapshot of what the access token might look like. The URL at the top represents the authorization endpoint, and the client ID is unique and assigned specifically to the client application, in our case, CoinApp. Per OAuth 2, the value of the scope parameter is expressed as a list of space-delimited, case-sensitive strings. The strings are defined by the authorization server. If the value contains multiple space-delimited strings, their order does not matter, and each string adds an additional access range to the requested scope. In our example here, the three scopes permitted by Piggy Bank are shown. Now, back to our flow. The application then leverages the access token for the resources from the resource server, as defined in the scope of the access token. No user credentials are ever exposed to the resource server. The same goes with the client application. The credentials are exclusively kept between the resource owner and the authorization server. Now that we just saw a brief overview of OAuth 2's authorization flow using the authorization code grant type, it's important to point out that OAuth is not an authentication protocol. The OAuth 2 protocol was built for authorization, not authentication. It excels at delegated authorization. If you wish to learn more about the authentication flow, please do take a look at another video in the API Academy video series titled OpenID Connect Overview. The option to log into a web application with your personal Facebook and Google account has become so common that most people now expect it for its convenience, ease of registration, and a seamless return experience. Social login can be implemented with OAuth 2, but its intent should not be confused with our authorization code example, where a social login platform can be used as a delegated authorization server for the retrieval of resources for an end user. In the case of social login, Platforms such as Facebook and Google are being delegated for application login only. This does not involve a connection to an independent resource server. Both Facebook and Google are just two examples of social providers. Third-party application developers interested in using their social login service would have to adhere to the requirements as defined in their review and approval processes. Knowledge check. Take a moment to answer the following question. When a client app registers with an API, what elements are being exchanged at a minimum? Choose the best answer. You may pause the video if you need time. The correct answer will be shown momentarily. If you selected choice B, you are correct. The client app owner must provide the resource API its name and callback URL before the API can return a client ID and client secret. The access token, while important in the authorization flow, is exchanged for a client secret in the actual flow itself, not at registration. So, how did OAuth evolve? The original OAuth standard, or OAuth 1.0, was created to address third-party authorization on the web. However, OAuth 1 contained various security flaws and limitations. Eventually, the OAuth specification was revisited and expanded to address a broader range of use cases and requirements in a new standard, OAuth 2. And it remains the best practice today to use OAuth 2. An authorization grant is a credential representing the resource owner's authorization used by the client to obtain an access token. OAuth 2 supports 4 grant types. They are authorization code, implicit, resource owner password credentials, and client credentials. Each grant type is optimized for a particular use case. As we go a bit deeper for each of the grant types, pay close attention to how the access token is issued to the client application. When using the authorization code, the client exchanges the authorization code for an access token. This was demonstrated in our example with Jane. And as demonstrated earlier, the resource owner's credentials are never shared with the client application and the resource server. The access token is never shared with the resource owner. While proven to be the most secure and most common grant type today, and as the hallmark of OAuth 2, its implementation is complex and requires plenty of upfront analysis and use case research. The implementer must still make decisions over interoperability, lifetime, and scope of the issued tokens, as well as other security and encryption considerations. OAuth 2, as a framework, does not prescribe standards for these considerations. And despite the authorization code's ubiquity, there is room and use cases for other grant types. In the implicit flow, instead of issuing the client an authorization code, the client is issued an access token directly. The grant type is implicit, as no intermediate credentials, such as an authorization code, are issued. The authorization server does not authenticate the client. The implicit grant is a simplified authorization flow optimized for JavaScript applications, particularly single-page applications, where the client secret cannot be shared or stored. While it is very much simplified in comparison to auth code grant types, the client application requires the implementer to customize it further for enhanced security, like validating state. As such, this grant type is recommended for internal applications and not for external apps or enterprise-grade solutions. With this grant type, the resource owner password credentials can be used directly as an authorization grant to obtain an access token. This grant type should only be used when there's a high degree of trust between the resource owner and the client. One such example of this trust is if the resource owner is the sole owner or operator of the device or physical machine that its native operating system sits on. Today, such legacy applications rarely exist. Most client applications today, operating systems included, are designed to access the web, which can readily expose itself to outside attackers. Nonetheless, given the nature of this grant type, the ability of a person to impersonate the resource owner is a core feature, which is a benefit if there is no desire to provide credentials each and every time, but a downside as this makes it incredibly easy for hackers to have complete access. Use this type only when other authorization grant types are not available. Client credentials, as an authorization grant, is typically used when the client is acting on its own behalf, or is requesting access based on a previously arranged authorization. Example use cases are typically for non-interactive applications, such as a command line interface, a daemon, or any service running in a back-end server that doesn't require any interaction with the end user. Many IoT devices also fall into this category. In all these examples, the client application would request and receive the access token without the user having any access to the protected resources. The client credentials can be used as an authorization grant when the authorization scope is limited to the protected resources under the control of the client, or to protect the resources previously arranged with the authorization server. Bottom line, client credentials should only be used as a grant type for confidential clients, or internal clients contained within a VPN or secure corporate network. Knowledge check. Take a moment to answer the following questions. Bucky Turner is an influencer who wants to use the MySocial application, a social media management portal, to view his activity and metrics across multiple social media platforms. It integrates with and extracts data from platforms such as Facebook, Twitter, and YouTube. In this fictional scenario, we'll assume that all three platforms provide MySocial and authorization code grant type to access their resources. After creating his new MySocial profile, he's asked to select the social media accounts that he would like MySocial to pull data from. He's currently active on Facebook, Twitter, and YouTube. For example, Bucky selects Connect with Facebook in the MySocial dashboard and is redirected to a Facebook-branded login page and logs in with his Facebook email address and password. He is then immediately presented with the following prompt. MySocial is attempting to access your Facebook account activity. Do you wish to grant it access? Bucky agrees and clicks the Yes button in response to the prompt. He is now able to see some vital statistics regarding his Facebook page activity and follower trends visualized on his MySocial dashboard. Identify the roles and components of this authorization process. Choose all that apply. You may pause the video if you need more time. The correct answer will be shown in a moment. If you chose options A, B, D, and E, you are correct. C is incorrect, since MySocial is the client application that is attempting to fetch the resources belonging to Bucky. Those resources are stored in the resource servers belonging to Facebook, YouTube, and Twitter. As Bucky connects the MySocial dashboard to each of these social media platforms for the first time, an OAuth 2 authorization code flow is executed for each. Evaluate the following statement. You may pause the video if you need more time. The correct answer will be shown in a moment. This statement is partially true, but the first sentence of the statement makes it B, false. It is true that the access token contains the scope, but MySocial will likely require at least 3 different access tokens, as each of these social media platforms are independent resources, requiring their own separate authorization flows. This also means that each access token would have a different set of scopes. Bucky is impressed with MySocial's capabilities. He returns to the application the following day, as he's curious about whether his Twitter feud with another influencer has gone viral and how it has impacted his follower ratings. As a login option, he uses his Google user credentials this time to log into MySocial. Which of the following best describes the login process with Google? Choose the best answer. You may pause the video if you need more time. The correct answer will be shown in a moment. If you chose option B, you're correct. Social login is sometimes confused with the actual authorization code flow, which would have already occurred when Bucky first set up his MySocial profile. While it may still be OAuth related, the login described here is strictly to do with Bucky accessing his MySocial account, which has been delegated to Google in this case. Oftentimes, applications will pass on the burden of maintaining a user ID and password database to established social media or communication platforms such as Google. In this case, Bucky consents to Google providing some basic information, such as name or email, to MySocial for authentication. A social login client ID is given to MySocial by Google, and a client secret is also shared between the two. As we can see, OAuth 2, while a huge step forward for authorization, is not without challenges. The main hurdle is its increased complexity. OAuth 2 has a reputation to be complicated and difficult to implement, not only because of the various grant types, but also because the specification itself is less prescriptive. It is, after all, a framework. The complexity is marked by the following characteristics. As mentioned previously, there are 4 different grant types, and while it's easy to cherry-pick the strong ones over the weak ones, the flip side is that they are even more time-consuming and resource-demanding to properly implement. And in some cases, you may want to avoid using a sledgehammer to crack a nut. Since its inception, the OAuth 2 core framework has been evolving, with OAuth contributors publishing additional specs to beef up the framework to make it easier for developers and architects to implement its authorization flows. Like other open-source frameworks of similar scale and magnitude, the long list of RFC specifications make OAuth 2 potentially overwhelming, as the reader is often left to figure out which of these specifications are interoperable, interdependent, or independent from one another. At the end of the day, the complexity price is paid by API providers, not the API consumer. OAuth 2 serves as a great guideline to bring your API program up to speed, and to mark that authorization checkbox. To help you navigate its complexity, it's highly recommended that you make use of reputable configuration-based implementation tools in today's API security marketplace. Whereas OAuth 1 described specifically how to implement a solution, OAuth 2 leaves much of the decision-making up to the API designer. For instance, while it provides a method for performing delegated authorization, it requires the developer to decide what the token should look like. While the token scopes can be customized to allow delegated authentication, OAuth 2 by its nature does not emphasize on the identity of the actual end user. This gap is filled by specifications such as OpenID Connect. Other items that are not clearly defined include how the resource server and authorization server interact, how the client registers with the authorization server, how the authorization endpoints are discovered, or the semantics of authorization scope. These semantics are often expressed in JSON format, but again, is entirely based on the implementer's decision-making. OAuth 2's open-ended nature has advantages and disadvantages. Leaving so many decisions to the implementer increases the possibility of security vulnerabilities and interoperability issues. But this has made it possible to build new specifications on the OAuth framework, such as OpenID Connect, which allows authentication via a third-party service. OAuth 2 has become a core part of the security stack for web APIs. If you need to control API access, this is the standard you'll want to use today. You've reached the end of the video, Introduction to OAuth 2. You should now be able to explain the purpose of OAuth 2 as a framework for authorization. Describe the authorization code flow. Summarize and compare 4 different authorization grant types. And finally, describe the current challenges of OAuth 2 implementation. Thank you for watching. We'll see you in other installments of the API Academy Learning Series.